So let's talk about reflections. Reflections. So what is a reflection? Can actually take you into the bathroom and show you that exact phenomenon. There's a mirror. Now you'll notice that the mirror image of my hand is the same distance away from the mirror as my hand is, right? And the other thing that's interesting about a mirror image is that it's what's called the chiral opposite of my hand. That means that although this is my right hand, in the mirror you'll see a left-handed image coming back at me. The same thing will happen when we use two-dimensional mirror imaging. For example, this is an example problem that we'll be doing later. You'll notice that it has flipped our triangle completely. And that's the same phenomenon as when you look in a mirror. Okay, so reflections, how do we deal with them mathematically? Well, the most common reflections that you'll see are reflections across the x-axis and reflections across the y-axis. So those are what we'll be doing first. So start by drawing your axes and labeling them, and putting an image on there that is not perfectly symmetrical. Put an image such as a sort of imperfect triangle, or something like maybe even a Z. A Z would work. In fact, I'll go with a Z. A Z is perfect. My Z looks just like this. Cool? Alright, so what we're going to do is reflect our Z across the y-axis. And you'll notice that I used Sharpie for this exercise, and I don't think that's a bad move. I think you should do the same, and here's why. What we're going to do is just fold our paper directly on the y-axis, if I have that skill. There we go. Good enough for me. Now that we've done that, we can hold it up to the light to find our new dots, our new points, and sort of Sharpie those in. The reason it's good to use a Sharpie is because it's bold and it'll bleed through the paper, which means that even though I marked the paper on the back, I still have my reflection dots on the front. And so I now have my mirror image of my Z reflected across the y-axis. So let's examine mathematically what that does to the vertices of our Z. What are our new coordinate points? You'll notice that it hasn't affected our y values. Sorry, I missed a parenthesis. It hasn't affected our y values at all. Our y values remain the same. What it has done is it's changed all of our x values from negative to positive. Or similarly, if we started with our positive anti-z, we would, or mirror z, or whatever you want to call it, we would get this negative z. So this is the effect of a reflection across the y-axis. All of your x-coordinates turn negative from what they once were, multiplied by -1. And the other thing is you have that mirror image chirality I was talking about earlier, where this slant is now going this way. Cool? Cool. Alright, so now let's reflect across our x-axis. Let me tell you the vertices that I am using. I'll just edit this part out, it's stupid. Okay. It ought to look something like that. Cool? Then we're going to, just as before, reflect across our x-axis by folding along our x-axis. So what is this done to the number values, the numerical values of each of our coordinates? Each coordinate's x value does not change at all, but each coordinate's y value goes from positive to negative, or vice versa, we could go from negative to positive. So this sort of gives us a good rule of thumb for reflections across the axes, which is most of what you'll see on the milestone test that you'll be taking this year, which is when you reflect across the y-axis, just turn your x values from positive to negative, or negative to positive, whatever they are, multiply by -1. Similarly, if you're going across the x-axis, you just multiply your y values by -1 and you get all your new values and you connect them the way that will create the mirror image that you want. Simple enough. What happens if we reflect across a line that is not one of our axes? Let's find out. Let's find out. For reflections across a line that is not one of your two axes, again, draw your axes, put a triangle on your paper. The line that I will be reflecting across is x equals 3. That means it's a vertical line 3 to the right of your y-axis. It should look something like that. So, just like before, we'll be folding, but rather than folding along our axis, since our mirror is at x equals 3, we will be folding along the line x equals 3. And putting our dots. So there's our mirror image triangle. What mathematically happened to our coordinates? Let's figure out what the rule of thumb is. Alright, so in order to find our rule of thumb describing numerically what's happening to our vertices, we have to remember that every point in our figure must be equidistant from the mirror as its mirror image. So I have this point on this triangle sort of corresponds to this point on that triangle, and they are each 1, 2, 3, 1, 2, 3 away from our mirror. Since we're reflecting across a vertical line, our y values will not change at all, but our x values must be equidistant to this line. Let's find this new point based on this initial point. About that, I had to re-record this part of the video because my microphone stopped working in the middle of taping last time. It was overloaded by math, as I'm sure that you are. So let's try and finish this off. We only have 2 more problems to do, I promise, and then we're done. Alright? So this is 6, 4. We need to get this point from this point, which is 0, 4, right? And the way that we do that, as we said earlier, we know that the two must be equidistant from the mirror, right? So this point is 1, 2, 3 away from the mirror, just as this point is 1, 2, 3 away from the mirror. So what distance is 3 away from 6? Again, we only care about our x distance, not our y distance, because y isn't changing. It's a vertical mirror. So we take our distance from 6 to 3. That's 6 minus 3 is 3. And then we double it to find the distance between our 2 points. So instead of saying 6 minus 3 is 3, we say 6 minus 3 is 3. 3 times 2 is 6. And our original point, 6 minus 6 is 0. So that's our new x coordinate. Here, 0. And this methodology should give us an idea of how to write out a formula that will give us exactly what we want from the get-go so that we don't have to fold paper and do all of this la-di-da-di-do-di-do to get our answer. So here's what we did on this problem. We subtracted 2 times the distance from our original point to our mirror. So we start with our original x value, x original, minus 2 times our original x value minus the x value of our mirror equals our new x value. So this might look like a bunch of gibberish to you. That's okay. You don't really need to understand the symbols as long as you see what I'm saying and how I apply it. Here's what I'm saying. In order to get our mirror image x final, what we do is we take our original image's x value. We subtract 2 times our original image's x value minus the x value of our mirror. Here's an example. If we look at these 2 points, we can go from either one to the other. Let's start with this one, the positive 9, negative 2 point. So from this point, how we get to this point is we start with our original equation, this 9. We subtract 2 times this original 9 minus our mirror value, x equals 3. So 9 minus 2 times 9 minus 3 equals 9 minus 12 equals negative 3, giving us this value. The same value that we got from literally folding the paper and putting dots down. This is just the formula, the mathematical formula to get it. Cool? Now let's try doing the same thing with a horizontal axis that is not our x-axis, right? So here's our mirror. This mirror is the line y equals 5. It is 5 units above our x-axis. And the triangle that I'll be reflecting across is this triangle. Again, you can do this with any image. It might just be easier to copy the points that I'm doing. But put your points down, draw your image, fold it, trace it, it bleeds through. You've been doing this for, I don't know how long now. This is what, our 5th or 6th problem. It's our last problem, if that's any consolation to anyone. Cool? So here we go. Now we need to find how we get this mirror image point from this original point. And again, it can be vice versa. If this is our original image, this would be our mirror image. So, as we know, our x value won't change because it's a horizontal mirror. And we know that it must be equidistant from this point to this mirror, and from this mirror to this point must be the same distance. That's just how mirrors work. So, find this distance from this point to the mirror. This point is at 1, this mirror is at 5, so that distance is 1, 2, 3, 4, right? And this distance must be another 4, 1, 2, 3, 4. So that means that to get from this point to this point, we must add 8. Simple enough. We can similarly write a general equation just like we did for our x, right? And it'll look basically the same way. We have our original y minus 2 times our original y minus the y value of the mirror gives us our final y value of our mirror image point. Oh, wait, let me get that in frame for you. As you can see, this formula looks very much like this formula. So if you are able to apply this formula, you should be able easily to apply this formula. Let me show you how we apply this formula to that point we had earlier from this positive to get to this negative, our positive y value, because y is all we care about, 9 y initial 9 minus 2 times y initial 9 minus our mere y 5 here equals 9 minus 2 times 9 minus 5 is 4. 9 minus 2 times 4 is 8, gives us 1, which is our new mere value, which is what we get when we fold and trace our image. So these general equations, these two general equations, are what we were basically deriving this entire time. These equations work. This one works for a vertical mirror, including the y-axis. The y-axis is a vertical line. Of course, we know it's easier to do the y-axis than any other point because our mere value, where is it? Here. Our mere value is 0, so it'll just be a number minus 2 times itself, which just gives the negative value of a positive number or the positive value of a negative number, right? Similarly, this is a horizontal mirror. These are the general equations for reflections about a vertical mirror or a horizontal mirror, given any sort of point. And now you know how to make reflections. Way to go! Whee!